Sounds great. Hello, everyone. It's lovely to present to you today. My name is Francesco Ciriello. I'm a lecturer in engineering education at King's, and I particularly focus in the way we teach design to students. This is Antoine. He's one of our undergraduate students, and he's been working with me on the SeedCorn project I will present today. The focus on the talk will be on how to enrich CAD models with data sets that entail the whole life cycle of the actual materials and consumables we use within design modules. And we wanted to acknowledge quickly support we got from the network, but also from Autodesk in terms of the expertise for model-driven engineering on CAD models. So the project started somewhere around here, where we took a CAD model of one of the systems that are developed by our students. It's a small remote control ship that has to collect floating waste within a pool. It's a simple project that students do in their first year. And we were quite excited that Autodesk launched a partnership with a company called MakerSite from Germany that specializes in automated LCA for CAD models to improve the way we actually make decisions for sustainable design. So that's where we started. We wanted to try and understand if this decision support system could be used within our teaching, if it could be a nice way of connecting the world of models in CAD space and how we design the geometrical shape of parts and manage components within our projects with the actually quite lengthy process of creating life cycle assessments for every single component that we use and deduce metrics that are useful when we're making design decisions. So that's where we started the project. We tried to evaluate the project as the first part of the SeedCorn, and we realized that if we were to make LCAs manually and compare them to the results of this tool, we were off by several orders of magnitude. So we realized, well, let's try and understand what can be done here in terms of improving this process. So I'll describe that a little bit and show you a little bit of the journey that we took. And crucially, what has driven us is the desire to meaningfully connect the sustainability of products with the way we design and the way we teach design. So we came up with some principles for what an automated feedback system would entail and how it could help students. And we typically articulate it like this. We start from the actual model that's developed by students. We then try and get students to think about the various inputs to the model, and we use a combination of parametric, symbolic, and configuration/variant management techniques within the CAD software. We would expect students to query the artifact and its evaluation and output some analytics in terms of visualizations at different scales of errors, warning messages, and decision-making tools that we can operate at the system level. We then wanted to build in tools to iterate and perform comparative analysis and track the design history that students would go through so that we can actually understand how they make decisions from CAD models. And finally, understand also how to feed back some of this material into their workflow via different types of reflections, orienting them towards documentation so they can better understand the sustainability metrics in design. And finally, ideally, we'd create a model that could also be customized based on the activities and learning objectives that we want to create. And that's the big picture vision of what we really want to achieve. And at this point, we're probably around here, where we're able to take a CAD model, extract its KPIs in terms of cost, performance, dynamics, and sustainability measures. We can vary a few of the hierarchy's components and then generate some feedback. That's where we are. So we'll talk today a little bit about what we mean by sustainable design pedagogy. We'll then move on to what the modeling requirements for a CAD model that works with our system look like. Antoine will then show us some of our most recent developments in terms of creating LCA for all the components within our modules, and understanding those requirements and what can be used to make this. So within our engineering program, we use model-driven development continuously for our many modules. It helps us to go from models all the way to build and test activities to motivate learning. We can also validate experiments and analysis and some of the simulations we run so that we can get students to better understand why they're modeling in the first place, as well as develop practical skills in terms of modeling literacy. And there's always a tension within the activities we create between how exemplar they are, as in how representative of real world they are, and how good the problem is, in that it constitutes many different faces and it's a nice set of trade-offs, versus how authentic it is compared to the actual things we go on and make and the impact that they have. And there's also a lot of tension between the support structures we create and the creativity and ambiguity of the spaces that we want students to explore. And in engineering design, I'm going to simplify it a lot. We tend to communicate via requirements and specifications. So that's definitely something that we ask students to present. But mostly we communicate through models, and in particular when we want to go and make parts, which is a substantial part of the activities we run, we have to present technical diagrams to a standard so that they can be made. So we'll look at these models and talk a little bit about why they're really interesting and rich and a really exciting place to do model-driven engineering. So a CAD model that students might typically develop is composed, of course, of geometries and transformations. We can export it as a bunch of STLs with transformations in 3D space relative to each other, and that has some of the information, right? But it's also got a hierarchy that will have to be developed by students, and this hierarchy will have multiple levels, and it's somewhat arbitrary how many levels are created by a designer. Each component, or actually each solid body within a CAD model, is associated to a material, and these can vary and will have different properties like density, cost, and whatnot. Finally, these materials will create, via an understanding of the geometry, certain physical properties that are really important for design, such as mass, inertia for the ship, centers of mass, which are all important dynamical parameters when you actually go and simulate the ship. And our approach has been to try and make the experience as authentic as possible for students. So what we've started doing is curating our own virtual component library of every single component we have in the makerspace, from the couplers to the fasteners to larger objects. And here's a sort of bird's eye view of the kind of components we have, from shaft sockets, couplings, to machine gears, to more specialist components like propellers, electrical components, motors, as well as stock materials that we use for fabrication and needs to be crafted and changed. And we were driven by the idea of, can we automatically retrieve information from a CAD model, so that we can then do data-driven analysis from it, and can we start first from our virtual library of components, and then move on to an actual novel design we can really predict from a student, who will contain a combination of our own components, but also fabricated parts of different materials. So I thought this is a nice problem to present to you, and I wanted to move on to a little bit about what the actual data structure looks like underneath a CAD model. So this is, I'm sorry it's a bit cropped off. This is a link that's openly accessible to anyone. It's the GraphQL schema of a CAD model developed in Autodesk Fusion. It's really not my intention to show you a spaghetti diagram that's too hard to read. I'm going to drill into it, but it's something that can easily be explored and investigated by you, and it simply explains how to query the model. The actual GraphQL schema and the information we are looking for can be better understood with hopefully this slide. We'll start with a hub, which is the team that you're working in. You'll then have several projects within that team. And each of these, of course, have IDs that you can use to identify them. Within each component of a project, which is the top level of, say, a design, you might have properties, you have several properties, but you'll have properties such as names, materials, costs, physical properties as well. And physical properties are really what we're interested in. Because we can then extract a mass density volume area, bounding boxes, which are really important for manufacturing. So we started thinking about some of the properties that we would need to be able to assess the sustainability of a part that maybe might need to be machined from stock. Maybe it's a part that we already know the impact for. And there's a lot of richness to the problem. So here's a very quick example for reference. Of course, you'll be able to see it later, where we have a GraphQL schema simply for physical properties on a component. And all we need really are the IDs of the project and folder, and of the and we can look at, say, quickly calling just the information we need with GraphQL for, say, the mass of every single component. And that can be useful because we can then extract from a very rich architecture just the stuff we need. So this seemed like a promising avenue to start building up our data enrichment process, because we can just extract this as a JSON file that we can then easily process. For example, one thing we started doing, just for our own ease of use, is importing the JSON into Excel, and then extracting the information that we need, including the component, material, and mass. You'll probably notice here that a lot of the materials aren't quite right because they use nominal values for components. So there's a lot that needs to be cleaned within the student's model actually to get it working. So that's definitely a challenge. And we can do this process recursively within a given component, so we can expect different levels of the hierarchy of the assembly. So, for example, in this particular call, we're just looking at the first level of the component, and we might define things like the model, its parents, its components, its material, and maybe some value of mass. Likewise, we can keep doing that up until 23 levels. Okay, so let me tell you how Antoine has been working on enriching some of our data collection strategy and matching it to the CAD models via extensive LCA work.
Hi. So the way we've been doing this is, now that we know that we can use GraphQL, it's actually eased up our method quite a lot with those models, and we're trying to enrich our data sets. To do so, we use mainly two types of data sets. We have one main database that the system runs on. It contains all the mechanical properties of our components, but it also holds the results from the lifecycle assessments, which we're going to talk about later, of those specific components. So we're talking at the component level. And at the same time, we can also use GraphQL to allow students to create their bill of materials that includes the hierarchy of every single component within that assembly. And so we can start working at the component level to try and get an LCA started. And so these are the modeling requirements we actually need to jump from a CAD representation or a CAD model of a component into LCA. And so as we can see, most of the input we can actually fetch and gather using GraphQL because it is a powerful tool that we can use to allow us to fetch all that data. And it allows you to create that powerful database that we rely on, which contains all of the information that's contained in the outputs, including all those impacts assessments. So before we jump onto lifecycle assessments in the context of our project, I'd like to define the 5 KPIs that we have chosen. We've chosen these 5 KPIs because we believe that they give students the right amount of insight into their project. It's not overwhelming, and it represents quite nicely how their projects or prototypes impact the environment, or how energy goes into actually making those prototypes. And so we use global warming, acidification potential, ecotoxicity, which is a human-related environmental impact, but we also use water use and energy use. And so before we jump into the LCA, I'd like just to show you the LCA framework that we'll which is a set of steps that we can use to always make sure that we can track our analysis and that we can reproduce it within our module. So if we need to update that database, we have a set of rules that we can follow. And so we always start by having a goal definition, a scope definition where we decide on the boundaries of our system, so how far we want to take that analysis. And then the software performs the inventory analysis, so it lists all the inputs that are needed and all the outputs. And then it's able, using a few impact assessment methods, so recipe 2008 or impact 2002 plus, use the results from the inventory to calculate all the actual impact assessments. And so we start to get a hint at how challenging it might get, because if we think of electromechanical components, we don't have an actual set of rules that's predetermined. I always use the example of making a cake. We want to make a cake, we know what it looks like, but we don't know the ingredients or the amount of ingredients we need. So today I just want to show you an example for a fairly simple component and something that we use quite often and that you have seen on most of the CAD models that we have presented before. It's the plywood sheet. And so we'll follow the exact life cycle assessment just for that 600 by 300 millimeter sheet of plywood. As you can see, we're following a cradle to gate approach, which means that we only take into consideration what happens when we make the sheet of plywood. So you can see we take into account the raw material extraction, the energy, the byproduct, and we disregard everything that's use phase and the end of life of the product, because we situate Kings around this point. And so we also take into account transport within the manufacturing and the creation of the plywood sheets. Now that we have this and that we have fetched all the data from the components, we can actually map this process into OpenLCA, which is an open source software that we can use to get results for both LCA and LCIA. See, once you decide the database that we use, so because OpenLCA is open source, we can choose whichever database we want, but we usually go for EcoInvent because it's the one that's got the most processes. We can then start and have all our inputs using different units. Here for the plywood sheet, we can just choose volume of our plywood sheet. And EcoInvent goes and already creates that recipe for making the plywood production. So you can see it takes into account markets. So it takes into account markets for actually extracting the materials, but also transporting them. And markets are default activities from known supplier. That's what's really interesting with EcoInvent, is that they work directly with suppliers to validate the data that we use. We still do validate our own data with literature-backed research, which is why we use the frameworks that we can compare papers qualitatively. So yeah, this is the process diagram for plywood production. And after running this, OpenLCA gives us an Excel sheet that we're able to gather data from and merge with the very first data sheet database that we got, which was full of the mechanical properties, hence creating that big final database that our system relies on. This is an example of the database without before inputting all the OpenLCA derived results. You can see we've got the part ID, the category, the name, the supplier, and the supply link. And then using GraphQL again, we can combine that first database with our second database. So I believe this is the first database that we showed you earlier. Now we are able to use fuzzy matching so that we can actually combine the two databases. And this is how we do it. This is an example, so sorry again, it's cropped, but this is an example of the very final way we want the system to look like. So this is the interface. So on the right side, you can see we've got all the inputs and the component tree diagram so that you can see all the assembly levels. But then at the middle, you have a 3D model representation of your model that's got a color-coded scheme to show you which parts are contributing the most to a certain impact assessment. And then on the very right side, you have all the outputs. And at the bottom, you can have some automated design feedbacks, such as prompt, improvement opportunities, and savings. But I do want to repeat that the example for plywood was a fairly easy one. If we start to dive into electromechanical components, we have to start using data sheets, which are not always meant to be used for an LCA approach. So an approach I did was I opened up a DC motor that we used and I weighed every single component and I tried to map everything onto OpenLCA, just like we did with the plywood. So that's kind of the challenge. Now, the next step is that we're trying to merge all the student CAD data with our virtual component library and database. And we also want to finalize creating the visualization app for decision making. That means we want to talk to students, we want to talk to module leaders to tell them what they actually want to gather and get from that visualization app. And we also want to design the visualizers so that they are meant to be used in a school setting and in an education setting. And we want to try and make sure we can validate our data because, as we said earlier, we did get some values that we could not validate. So right now I'm going into literature just to try to get all that data to compare. So thank you very much for listening to us.